Hello, good morning. I'm your speaker, Gabriel Adih, and today we're going to talk about preparation and characterization of geo-based polytriaxyl composite and their application in H2S gas sensing, which is advised by Dr. Jeremiah Milyari. So we start with the introduction. So H2S or hydrogen sulfide is a toxic colorless and flammable gas that has a rotten egg odor and also detectable at low concentrations. Its hazardous effects are eye, nose, and throat irritation at 10 ppm maximum and respiratory failure at 100 ppm maximum. So, sources of exposures are oil and gas industry, wastewater treatment, mining and geothermal operation, volcanic emission, and decomposition of organic matter. So, common conductive polymers used in gas sensing are polypyrrole, PDOT, polyaniline, and P2H3. So what are the advantages of P3HT? High conductivity, mechanical flexibility, and easy to process. Its applications are organic field effect transistors, or OFFETs, or solar cells, and gas sensors, as stated before. Background studies also use P3HT for gas sensing, like P3HT Porogen Hybrid for better NO2 sensitivity, P3HT polystyrene or PSS that improves ammonia selectivity, and then MOS2 or molybdenum disulfide integration will enhance the charge transfer and recovery rate of P2HT. So the research objective of this topic is to develop P2HT graphene oxide composites for effective hydrogen sulfide gas detection. So they evaluate the key sensor performance metrics are sensitivity, selectivity, repeatability, and stability. The characterization techniques are water contact angle, which will analyze the surface wettability and interaction. SEM, or scanning electron microscopy, will reveal the film morphology. XRD, or X-ray diffraction, will determine the material's crystallinity. Then FTIR, or Fourier transform infrared spectroscopy, will identify the functional groups. So the applications and relevance. For application, it will have industrial safety and environmental monitoring. Then it will support the SDG 13 climate action and SDG number 9 innovation and infrastructure. So for the methodology, we start with the 25 hours room temperature mixing and enter environment. Then it will be precipitated in methanol for 1 hour to stabilize the reaction. For the cleaning method, we will have 3 times the methanol, 10% HCl, acetone, ammonia, and dry water, which will then be uh, oven dried for 12 hours at 55 degrees Celsius. So the preparation of GO, so oxidation reaction, graphite is treated with strong acids. Then reaction termination, mixture is diluted with water and quenched using hydrogen peroxide. For the washing and purification, it will be washed by hydrochloric acid and deionized water using centrifuge separation, and it will be repeated 4 times per liquid. Then for the drying, GO is dipped with liquid nitrogen and freeze dried for 4 days. The final product will be a brown color GO powder, and it is ready for composite film preparation. So for the preparation of ID setup or interdigitated electrode for the gas sensing, first is the substrate preparation. We will clean and prepare the ITO glass substrate. Pattern engraving, we will use the BMO laser machine to engrave the ID pattern onto the ITO glass, which is seen in the figure on the right. It will enhance gas interaction and electron transfer. For the next is the composite film application, preparation of the composite film solution, which is the P3CGO blend, and act as a binding agent for the gas sensing layer. Then for the film deposition, it will be drop casted onto the solution which is patterned on the ideal glass and allow it to dry. So for the gas sensing mechanism, gases flow from cylinders through flow controllers. Then it will enter mixing chamber for even blending. Then it will flow into sensing chamber with the IDE sensor. Then the source meter will measure the electrical changes from the gas interaction. Then the thermometer and hygrometer will monitor the temperature and humidity of the room. Then the gas exit through the gas out line into the waste collection tank. So here's the material characterization to support the gas sensing as mentioned before, XRD, WCA, FDIR, and SCM. Let's start with the results and discussion. So on the black line, we will see the pure PTHC will have a carbon to hydrogen stretching, which is the alkyl chains will appear in 2900 to 2800 range. Then it will bend at 1660 range. Then a carbon to sulfur stretching will be the typhine rings will be found in the 800 to 950 range. Then in the red line, which is the P2H2 GO, new peaks will appear due to the GO functional groups. A oxidant to hydrogen stretching, which will be found at 3400 to 3200 range. Then we will have a amide group in the 1660 range, and then the carboxyl groups will appear in 1100 to 700 range group, which is the geofunctional groups. Then for the cross-section SEM images of the composite film, which is the pure 0.5 weight% added geo and the 1 weight% added geo. So observation, we will have a smooth and homogeneous surface, which indicates pristine conjugated polymer structure on the pure one. Once we added the 0.5 weight% geo, we will see the partial coverage of geo, which some regions will still exhibit a polymer-only morphology. There's also a uneven distribution of geo to the geo limitation of the dispersion. But once we added the 1 weight%, a nearly continuous geo layer, this is due to the geodispersion and interaction with the polymer, which is also caused by the pi-to-pi stacking and hydrogen bonding. So here's the XRD graph of the polymers and polymer composite. So we start with the pure one, which is the black curve. Sharp peak will be found at 5 degrees to 5.5, which is the 001 plane, and lamellar stacking, which is the alpha phase of the polymer poly-3-hexyltyphene. Then the broad peak will be at 20 to 22 degrees, which is the 010 plane, which is also the pi-to-pi stacking after geo is added, which is the red and blue line curves. 001 plane will remain, which is also the lamellar structure retained. But the peak intensity will decrease and broaden, reduce crystallinity and disorder due to the GO. But 010 will indicate that pi-to-pi stacking will be still observed, but there will be no distinct GO peak, means that it is well dispersed onto the polymer surface. Then for the pure P2H water contact angle will have a 117 degrees. Then 0.5% added GO, we will have 113 degrees. And then 1 weight%, which is the 95 degrees. So it will all show behaviors of hydrophobicity, meaning they eject water on their surface. So the decrease in contact angle means it becomes more hydrophilic as the GO% increases, meaning that the GO functional groups will interact with moisture and water much better. So here's the application. We start with the gas sensitivity performance of pure P2HD. So at 1 ppm, we will see the 26% response, then 5 ppm at 41%, then 10 it is at 47%. This means that P2HD responds at gas levels which is increase in concentrations. But as we can see the 0.5 weight%, it is slightly lower at 1 ppm, only about 2%, but it increases at 5 ppm, which is at 26%, then 10 ppm at 37%. This shows that adding small amount of geo reduces the initial sensitivity of the composite. This is due to the changes of the charges and interaction of the surfaces. But there is a big change when we add 1 weight% geo. As you can see in 1 ppm, the response is already at 11%. Then at 5 ppm, it jumps to 65%. And at 10 ppm, it reaches 105%. So the big improvement means that more geo helps the sensor a lot. So geo adds more active sites and improves how well the material detects gas. And this makes the gas sensor much more sensitive. Here's the repeatability performance of the pure and P3HC geo films. So pure P3HC is the lowest response in all three cycles. This means that less sensitive and less consistent compared with the geo composites. When 0.5 weight percent is added, the P3HT its response improves in all cycles. This is because graphene oxides provides more active sites for gas to stick to, which will help the sensor detect hydrogen sulfide more effectively. So it is a clear step up from P3HT or pure P3HT. At 1 weight percent geo, the sensor shows the highest and most stable response in all three cycles. This is due to the synergistic effect of the geo, which has a large surface area and functional groups that help absorb gas better. Also, there is a strong pi-to-pi interaction between geo and P3HC, which improves how fast and efficient the gas sensor reacts to gas. So the gas selectivity performance of the pure P3HC and P3HC geo. So the selectivity behavior of pure P3HC and its composites with GO reveals a distinct shift in gas response. Pure P3HC shows the highest selectivity to SO2 due to the strong charge transfer interaction between SO2 and the pi-to-pi conjugated thiophene rings, which enhances Hall concentration and conductivity. However, when GO is incorporated, especially at 1 weight percent, the selectivity shifts significantly towards H2S. This is mainly due to the presence of oxygen-containing functional groups on GO such as hydroxyl and carboxyl groups. These groups act as active adsorption sites, promoting stronger interaction with H2S and facilitating efficient electron donation to the sensing film. The high surface area of GEO combined with these functional groups enhances gas adsorption, while pi-to-pi interaction between GEO and P3HC improve charge mobility and sensing response. Although GEO enhances H2S sensitivity, it can reduce SO2 detection due to the possible blacking of active sites on P3HT and changes its electronic structure. Overall, P3HT GEO composites um, demonstrate superior selectivity for H2S, while PPTHC remains more responsive to SO2. For the conclusion, GO improves the chemical and sensing properties of P2HC, which is confirmed at FTIR, as stated in the new functional groups, enhances surface reactivity for better gas interaction. Structural and morphological changes observed in SEM as GEO increase the layered in interconnected structure (XRD). Crystallinity decreases but indicates structural modification, which is the strong pi-to-pi stacking and hydrogen bonding, improving the mechanical and electrical behavior. So hydrophilicity increases with GEO content. So contact angle measurements show better wettability and helps in gas adsorption in response in sensors. So significant improvement in gas sensing, pure PTHC response to SO2. Geocomposite shows high sensitivity to H2S or hydrogen sulfide, which is at 292% shown in the gas repeatability and will provide more active sites for the polymer and better charge transfer. Then the durability enhanced with GO, it shows that it has a great and long-term initial performance due to the cycles, and which will offer enhanced conductivity and protection, which will reduce gas sensor degradation. So that is all for the topic. Thank you for listening. Have a great day.